Hey everyone, I'm Arsha Niksa, and in today's video we'll be talking about the bisection method, which could be utilized to solve single variable equations. So let's say you have a complicated equation like this: sine of x plus cosine of x2 is equal to 3. And you want to find the x's that satisfy this equation. So for what x's this equation could be satisfied? Now, you could take 3 to the other side, then you will have e to the power of x sine of x plus cosine of x2 minus 3 is equal to 0. Now, this is a function of x, let's call it f of x. Then the problem would basically become a problem of finding roots for f. Because if x satisfies this equation, if let's say x satisfies equation, then x is a root of f. And conversely, if x is a root of f, this we could go to the other side and you would know that x in fact satisfies the equation. So if you know how to find the roots of an arbitrary function, arbitrary continuous function, then you would be able to pretty much solve any equation that you want, provided that it is continuous. So in order to solve this equation, we would have to find the roots of its corresponding function. And in order to do so, there are many methods, but one method, which is numerical, is the bisection method. The bisection method relies on something called the intermediate value theorem. So we could go through the precise statement of the intermediate value theorem, but for simplicity, we'll just talk about its result. So let's assume that you have a closed interval like a to b, and you know as a fact that f at b is positive and f at a is negative. And you also know that f is continuous. Then there would be at least one root in the interval a to b. In other words, if this is the x-axis and this is the y-axis, f has to at least pass through the x-axis at least for once. So it could be like this, it could be like this, it could be like this, and so on. But it would be impossible for f not to pass through the x-axis. Now you might wonder, why should f be continuous? Let's assume that that's not the case. Then, you know, f is positive as b and is negative as a, and you could have a jump discontinuity at, let's say, x naught. And basically, you could provide an example of a function that does not pass the x-axis, but does satisfy the conditions of the result of the intermediate value theorem. So this is the idea behind the bisection method. So let's say you have a function like x3 minus x minus 1. Now, of course, you could try to find the solution analytically, but in order to do so numerically, we would utilize the bisection method. Let's say you know that there's a root in the interval 1 to 2, and you want to find where the root is. So you look at f of 1. So if you calculate f of 1, that would be minus 1. And you also look at f of 2, which is 5. And you basically see that at 2 we have a positive value, but at 1 we have a negative value. So this is minus 1 and this is 5. So there has to be at least one root in this interval. Let's call this root x of r. So you want to find what the root is. In order to do so, you would bisect your interval. So you would find the middle point, which is clearly 1.5, and you would look at the value of f at 1.5. So if you do so, that would be, yep, that's right. So this is positive, so it would be something like this. And now let's again get back to the intermediate value theorem. In this interval, the function could be completely positive, so it does not necessarily have a root. But in this interval, it has to have at least one root. So we turn our focus to this interval, which is 1 to 1.5, and repeat this procedure. So we would just look at its middle point, 1.25. We would calculate 1.25, which is a negative value. So this is something like this. So these two are negative, so you might not have a root here, but you do necessarily have a root here because this is negative, this is positive. So you turn your focus to this interval and you repeat this procedure. You calculate f at this middle point, x of n, and then you see if it is positive or if it is negative. And if it is negative, then again you turn your focus to this interval, to your right interval. And if it is positive, then you have a negative one here and you have a positive one here, and you have to turn your focus to this interval. So you would have to look at this interval. Now the point would be that you could repeat this procedure, let's say n times, and by doing so you would get to a very small interval, something like this. Now, as an approximation, now you know that x of r is necessarily in, let's call this interval I, is necessarily in I, and let's assume that I is like this, AI and BI. For example, let's say, I don't know, 1.348, no, this should be 3 and 1.3248. Now, as an approximation for x of r, you could take the middle point of this interval. So it would be the average of its endpoints, and thus you would have an approximation for your roots. So now let's review what just happened. You had an interval that you knew that there was a solution in, or at least you guessed there was a solution there. So let's say 1 to 2. And then you bisected the interval once. You looked at the sign of its middle point, and then you basically saw how that was different from its values from this one and this one. And based on that, you chose an interval, right one or the left one, based on whichever interval necessarily had a root. So let's say it was the right one. Then you again repeated this procedure. Then you again, and again. And you could see the intervals are getting smaller in the order of 1 over 2 to the power of n. So this is basically a very fast algorithm. So by doing so, you would get to an interval, a very small interval, small I, such that the root x of r is necessarily in this interval. And when you get there, you could basically take the middle point of I, which was AI plus BI divided by 2, as an approximation for x of r. And this way, you would have a numerical approximation for the solution of your equation, which was basically converted to its corresponding function by taking everything to one side and creating 0 on the other one. So yep, I guess that's it for the bisection method. Hopefully in the next video we'll be covering the coding part for the bisection method. Have a nice day and bye.